Great, why don't we go ahead and get started? So welcome back everybody to EE240. So just a few sort of administrative kind of things before we get started. As I'm sure you guys know, homework number 2 is due today. Hopefully you guys are basically done with that. Just one, not necessarily huge thing, but one thing which somebody had asked about, so just to clarify, the diffusion length for our technology, meaning the LD that you should use in your source drain areas, that's quarter micron, meaning 0.25 micron. If you used a micron, then obviously your life was harder than it needed to be, but that's not the end of the world. From now on, just use quarter micron and that will basically be fine. So if you already turned in your homework or you're done with it or whatever and you used 1 micron or something else, that's fine. Just moving forward, stick with quarter micron. So the other thing is I posted homework number 3 up on the web yesterday, so you should definitely take a look at that because that's actually going to be due 1 week from this Thursday. And one of the reasons for that is that the midterm is basically coming up essentially, I think, about a week after that. So midterm's definitely coming up pretty soon. Basically next Tuesday I'll kind of give you guys an update on what's the material that will be covered and when we'll do review session and all that other kind of good stuff. But just keep that in mind because that is coming up pretty quickly. Just one other sort of quick administrative thing. I'll actually have to leave sort of immediately after class on this Thursday to catch a flight. So I won't be having office hours, but Pierluigi will be doing his sort of standard discussion session tomorrow. If you guys have any questions, again, please feel free to send me an email. So, any kind of questions on either material so far, or homework, or logistics, or anything like that? Okay, so hopefully you guys are all caught up to date. By the way, how many of you guys are actually done with the homework? Okay, so I take it if you're here, that means there was a good chance you were done. Okay, well, so let's go ahead and dive back into our material. So last time we were basically just, oh yeah.
I was just wondering, how accurate is the spice simulation for the flicker noise, like at low frequencies?
So are you trying to use it to match with the numbers that I gave you from the handout, or you're just checking that you just want to know in general, is it? So the answer is sort of as usual, it all depends on the model, right? So it depends on whether the person who actually created the model tried to do some measurements to really correlate their model against that simulation. So for our particular model, the thing you need to keep in mind is this is a totally predictive technology, meaning there's no real transistor associated with it. So the question is somewhat, how should I say, or the answer I should say is somewhat ill-defined because there's no real transistor that's associated with the model that I gave you to actually check it against. But from the standpoint of this class, you can assume that whatever spice actually gives you is halfway reasonable. Now, obviously, if you've done some simulation, you see something that looks totally bogus, then come bug me or send me an email or something like that, and I'll tell you, okay, yeah, no, that's really some bogus thing in the model versus that's probably reasonable. So was there some behavior you saw that was?
No, just in general. Like I was not asking for predictive models, but in case like if you use the fab models. So I was just wondering like how accurate they are.
That is something that in principle they should be looking at. So it's as accurate as the rest of your model is accurate. I'll put it that way. So if you know anything about what I usually trust in terms of the models, that would give you an idea as to how accurate it really is. But again, it is something that they generally will look at. So there should be some correlation with the reality there. But by the way, that's just an example. That's why we talked a lot about corners and process corners and things like that. Because my general philosophy is that it's not that I necessarily believe what the model is, but I do believe that if you will move your circuit around into a bunch of different corner cases, if things all still work in those different corners, you have a pretty good shot that the real thing will actually work, even though each of those individual models might have been somewhat bogus. Does that answer your question? Or? Good. Other questions? Or? Okay, so why don't we go ahead and dive back in. So last time we basically started talking about current sources, and we sort of took a slight detour in terms of talking about just, I'm going to have some big chip. That big chip is going to have a bunch of different things where you probably want some bias current in it. Let's say a bunch of different amplifiers all over the chip, right? So we basically ended up last time saying that if I had something like this, the way you're really going to want to do that is you take some pad, then you're going to locally mirror that current just to create the voltage. And then once you've done that, really what you want to do is create a bunch of basically local current sources, that then you'd feed each of those current sources into the local locations that you needed to use them in order to actually make sure that basically the relative voltage you're using is actually referenced to the point at which you're using it. Because remember, currents, those are sort of absolute. They always flow. Voltages, that's always A versus B. Okay? So just one other sort of really quick thing I wanted to mention before we move on from this is just, in a real, or I shouldn't say real, but most likely if you're here in school and if you ever build one of these chips, so usually the way you would do this is you'd indeed say, okay, well, conceptually this is some external current that you're going to be feeding in there. But a lot of the time, you may not even actually have an instrument or whatever. You just want to put this onto your board. So remember, simplest way to actually get a current is to just, let's say, put some resistor in there. And then either you can tune that resistance, or if you're really sort of clever, you could also put some variable voltage source over there, right? So just from a sort of very practical testing standpoint, whenever I build chips, usually this is the way I create my biasing network, just because if I do that, I have the freedom to both move around what that voltage is, because that's kind of completely external, and moving around what that resistor is there as an example, because you may want to make sure that you can actually make it large enough that it really does look like a current source relative to the 1 over GM of whatever it is you put on your chip over here. Okay, so from a practical standpoint, that's usually how I end up implementing those current sources, but that's really just sort of a side note for you guys that, hopefully we'll be building some chips sometime. This is, just a sort of fairly straightforward way of doing things. So any kind of questions on this before we move on, or? Okay, so I'm sure you guys have all seen current sources and current mirrors many, many times before. But now that we embarked on this whole long discussion about noise, there's some interesting things for us to actually look at from the standpoint of building those biased current sources and how much noise they're actually going to add into us. Now, given that we're talking about using a biased current, mostly what you care about is how much noise current gets added on top of that main current that you're interested in, right? Because if the output units is current, you probably care about current as how much noise is being added to it, okay? So if I just have the sort of single current source by itself, you can just go and figure that out pretty quickly, right? You just add your noise current in parallel with that. You could, you know what that'll be, and we'll actually take a look at that in 1 second. We have to remember one thing, which is if I'm going to do a current mirror like this, I'm actually going to have some noise from the mirror as well, right? And obviously, since I basically am doing some mirroring ratio over here, whatever noise current I have in that mirror is actually going to get multiplied up when it shows up at the output, okay? So if we just walk through, as an example, this particular circuit right here, I'd have, let's say, some noise current, which I've called ID1 from the mirror device. Actually, excuse me, ID1, so let me just label this. So I'll do it a little bit bigger so you can see. That's M1. That's M2, right? So if I looked at the noise current at the output, I would basically have the noise current from the main transistor, plus I'm going to have the noise current from this bias device, but multiplied by this M squared, where M squared is just the ratio of, let's say, the width of this device to that device. And by the way, when I say width, that obviously could also mean just, how many of those devices you put in parallel, right? Okay, so now, given that this is a current mirror, keep in mind we're probably going to bias these things up with the same V star, right? Because that's kind of the whole point of doing a current mirror. So actually, you can very quickly show, basically, the GM of this guy should be M times the GM of that guy, just because it's that much wider, right, or has that many more parallel fingers. So that means that essentially I can say that I have a GM1 over here for this device, a GM2 for this device, and then again, since I'm multiplying it by M in current, that means M squared in the variance. And so since I know that GM2 is just GM1 divided by M, because again, it's M times smaller, that's how you get from there to there, okay? But now if you kind of pay attention to this, this is a little bit bad, right? Why do I say this is bad, by the way? What kind of looks like it's not so good news about this particular noise current over here? How do you usually want to choose M?
Large.
Yeah, why do you want to make it large?
Minimize your standby power. Sorry.
Yeah, right? I usually want to use a pretty big M just because this thing over here is just a current mirror, right? It's not actually doing anything really useful, right? So if I make M large, that means that all of a sudden I'm going to get way, way more noise at the output of that device than I would have had, obviously, if I just had that device by itself and some magic voltage bias going into it, then this is the noise I would have gotten, right? So that's kind of bad news. Now, the good news is here that most of the time when you do this, you just have to be a little bit more careful, right? So, by the way, maybe somebody knows, and I kind of hinted at it already. So what I kind of said was that if I had some way of creating a magic voltage at this gate over here, where that voltage was totally stable, then I could kind of get rid of the noise that was getting amplified up from this bias transistor. So anybody have an idea? How can I create that? By just modifying the circuit slightly, or maybe adding something to the circuit?
Bypass cap.
Yeah, bypass capacitor, right? So basically all I really have to do is, if I add some nice big capacitance at that point right there, then effectively at any sort of, let's say, quote-unquote, reasonable frequency, this thing just, if I look back over here, the impedance is low, right? It should look like a fairly stable voltage source, right? To kind of think of it as another way, when I add that bypass cap in here, what I'm really trying to do is filter out all of the white noise coming from that bias current source, okay? And by the way, this is usually something you really want to do anyways, just because you really want this voltage right here, meaning the difference between the gate and the source, you want that to be really stable, right? Because if that's not stable, let's say there's some, bounce on ground over here. If that's not stable, that's directly going to translate into a change in the current at the output, right? So anytime you do one of these current mirrors, don't forget to add that bypass cap in, okay? By the way, now, even after you've added that bypass cap in, so, if you add that, then at least dynamically, you can largely get rid of that M factor. But just again, as another sort of rule of thumb for you to remember, you still probably don't want to make that M factor bigger than about 20, okay? Because if you go bigger than 20, you're just starting to ask for trouble, either from the standpoint of amplifying noise, or if there's any, as an example, gate leakage in the devices. If you make these really, really huge ratios, very, very likely that actually the current you get on the other side won't be what you really wanted it to be. So again, just, rule of thumb kind of thing for you to remember, one of those good things that stops you from being fired, stick with no more than a ratio of about 20, okay? Does this make sense to people, or? Okay, so now, let's say that indeed we've gotten rid of that M, okay? So we add some bypass gap there, we're good designers, we take care of that. There's still actually sort of an interesting thing to notice here, right? So what I'm going to get is essentially that the noise current is going to be something like 4 kT gamma GM, right? That's just the noise current from that M1 over there. Well, I can always just to sort of make things clear, what I want to do is redefine this sort of effective noise resistance. Okay, and again, just ignore this M factor over here. So remember, I can also say that a noise current is, for some resistor, is also equal to 4 kT over R. So I'm just going to define this Rn over here so that I get the same noise current as I get from the transistor. Okay, and I'm going to do this, you'll see why in 1 second why I'm doing this. Okay, so if I do that, then clearly Rn is essentially just 1 over Gm, right? But remember, the whole reason I built this thing was because I wanted a current source. So for a current source, what's kind of like the main property I care about if I sort of look back in that direction? What do I want to make sure is the case? Yeah, I want high output resistance, right? So in this case, if I had a transistor, the output resistance I get is just RO, right? Just the RO of the transistor, okay? But notice Rn is actually equal to 1 over Gm, right? In other words, I can kind of rephrase this as saying that the noise resistance is the same as the output resistance, but it's divided by the gain, right? By the GMRO. So, why is that kind of bad news? Why do I claim that that's bad from the standpoint of particularly noise? Any thoughts? If you want small noise current, do you want big resistance or small resistance?
Big.
Yeah, you want big resistance for small noise current, right? But here we just said that the noise resistance was whatever RO I got divided by the gain, right? Meaning that the noise I'm going to get is actually larger, right? The noise current's actually going to go up by a factor of GMRO versus, as an example, if I just threw a resistor down there, okay? So, this is actually going to lead us to a very interesting question. But the key point here, which we're going to see in 1 second, again, just we'll understand why we do things this way, is that if I'm going to build a current source, effectively that transistor is really boosting. It's going to give me a good output resistance, but it's not necessarily going to give me a good noise resistance. Okay, in other words, that active source, it's boosting the RO, but it's not boosting the noise resistance, okay? So now, usually at this point, somebody sort of says, well, wait a minute, what the heck is going on here? Because what I basically just said was that, and let's do the following comparison. What I basically just said was something like the following. So if I took this transistor and I somehow biased it up, and I biased it so that I had a small signal resistance of RO, and I compared that to another resistor over here, but this one is just a linear resistor with a value of RO. Okay? What I've basically just said is that this has more noise than that does. Right? And it has more noise by exactly GMRO. So now, here's the question for you guys. If that's the case, why do I ever bother using this? Why don't I just take a real resistor and put it down always as my bias current source?
You don't have the space.
Don't have the space.
Voltage, headroom.
Okay. So just, on the space side, I can probably build a resistor and a transistor. Okay, maybe the resistor is a little bit bigger. The real problem is the voltage headroom, right? So the trick is if I build a transistor as my current source, and let's actually go ahead and draw this. Right, if I draw the IV curve of that transistor, right, I'm going to get something that, let's say, looks like this, right? Okay, so out in this region, that's where I'm getting that good output resistance, right? But now let's say that I wanted to actually just replace that transistor with a resistor, but it has the same output resistance. Well, maybe I'll draw this in a different color just so it's clear. Now what I'd have to do is I'd have to take that same slope, right? And as you can kind of visually see, in order to get the same current, I have to be way, way out on the voltage, right? So the trick here is that the reason you often end up using basically bias current sources rather than resistors is that you'd like to be able to use a resistor, but you just can't afford that voltage drop, right? Because just like we said that effectively the noise here was larger by GMRO, roughly speaking, the voltage drop over here is also smaller by GMRO. Okay? So the real reason you use active bias currents is just that even though it boosts the noise, it's going to let you actually fit into a certain voltage headroom. Now, by the way, why is that important that I should fit into a certain voltage headroom? I mean, why do I care? Like, why not just have higher voltage or something like that? Okay. So you want to maximize the swing, right? Because remember, as we talked about a couple times now, I'm talking about noise here, but there's always the other side of the equation, right? So if I have a certain amount of noise, if I can get even more swing, then on the net, my signal-to-noise ratio might actually be better, right? So the point here is that I actually oftentimes want to use these active bias currents, because basically, even though I'm going to be multiplying the noise, I win by perhaps even more from a swing standpoint, okay? So that on the net, I might actually be able to get a better overall performance. Now, obviously, you have to look at the circuit itself to really figure out if that's true, but that's really why you end up using these types of bias currents, okay? And what this is really actually kind of getting at is that even with a bias current, actually, or in general, with any sort of biasing that you do, there's always going to be a trade-off between what's the sort of voltage drop you get across this thing, or similarly, what's the minimum voltage you can put on it and still have it act as a current source, and how much noise it's actually going to be adding into your circuit, okay? So just, that's kind of what I was sort of saying here, right? So basically, you know, if we kind of go back to our EE140 type of model, you know, we know that V star is not really the same as the overdrive or the VD-SAT, but we can kind of say that, okay, let's pretend that roughly those two are similar to each other. And we'll just handle that by saying that rather than like in a long channel device where we said that the VD-SAT was just equal to V star, now we'll just say that VD-SAT, which is what I'm going to call Vmin, meaning the minimum voltage or the minimum VDS you can put across that transistor and still have it be high output resistance. Instead, I'm going to say that that VD-SAT is K times V star, okay? Where that K is just sort of some arbitrary parameter that I've added in. Okay, it's something like maybe between 1 and 2. Okay, it depends on exactly, you know, the transistors and everything, but something like between 1 and 2, okay? So now what you can kind of quickly see is, if I've defined things that way, that basically tells me that the minimum voltage I need is obviously proportional to that V star. But the noise resistance, if I just change this GM to be equal to ID over V star, right? You just plug that back in over here. What you can see is that the noise resistance is basically going to be proportional to that Vmin, right? So again, there's now this sort of immediate trade-off that should be jumping out at you. Because if I want to make Vmin small to get a lot of swing, that means my noise resistance is also going to be small, which means the noise current is going to be larger, right? And of course, vice versa, if I want to try and reduce the noise, that means that I'm going to use a large Vmin or a large V star, which will increase the noise resistance, but will eat into my signal swing, right? So basically this trade-off that you're going to, you know, that we're going to keep on seeing, and that actually you're going to spend a lot of time optimizing in many of the amplifier designs you do, is just how low of a noise can you get versus how much signal swing can you actually get, okay? And as you'll see, a lot of times people really try and optimize the signal swing to be kind of as much as is practically possible, because on the net, that often turns out to be the cheaper way to get the same performance for a given amount of power, okay? Or I should say, to reduce the amount of power you spend for a given performance. Does this kind of make sense to people, or? So now, as is kind of highlighted on the slide here, right? If you had your choice, and if you could do sort of anything you wanted, then with a bias current source, you always want to use large V star, right? Because basically, remember, the noise current is always related to GM. And so if I just have a bias current, I want to minimize the GM of that bias current. And the way you do that is by using a large V star. Okay, but Again, of course, the trade-off there is that if you make it too large, you'll start losing signal swing. Okay? So, but generally speaking, from now on, usually people told you, maybe back in 140, you always wanted like a small overdrive there. Well, there's actually a little bit of a trade-off there. Okay? So just to really sort of make this very clear, it's a little bit instructive to actually look at what people do for bias currents, not just in MOSFETs, but actually in BJTs and other types of transistors as well. Okay? So here I've just drawn this sort of fairly typical bipolar current mirror. Okay, and we'll walk through the equations, or we'll just maybe touch on the equations in 1 second. But before I do that, it's kind of interesting to ask the following question. So notice in this bipolar current mirror, I added in these two degeneration resistors. Okay? So in contrast, you might say, well, why did I do that? Why didn't I just, let me build it. I'll kind of draw it, I'll go back over here and draw it. I could contrast that with, why didn't I just do kind of the same thing in bipolar as I would have done in the MOSFET? Right? So why didn't I just take basically two devices, tie one up as a diode, and then take that as my output current? What's sort of bad about that particular current mirror there? Anybody remember or have an idea?
Thermal runaway.
Okay, so that's the usual. So thermal runaway was the answer. Yeah, that's annoying. It's bad. Let's not even worry about that. I'm actually sort of even more zero order, I guess.
It's because of the base current?
Okay, so you're right. There's some base current that's actually flowing into there and flowing into there, and that's going to cause some error in my mirroring ratio. Let's even assume my beta is really good. So I don't know, I have a beta of 10,000 or something like that. I'm not worried about that. So you guys are both absolutely right. What else is bad about this?
Temperature, instability.
Yeah, so that was the thermal runaway, right? So if I do this particular current source, if I'm not careful, then actually across temperature, it could actually run away. But, so all that's correct, but I claim there's something, particularly from the standpoint of what we've been talking about, that's, more direct impact. So let's say I managed to solve all those problems that we've talked about. What else is bad about this?
Process variation in a bipolar is going to give you an exponential kind of...
Ah, okay. You've kind of hinted at it. So you said there's this exponential dependence of the current on kind of any sort of error that I might be making in that VBE there. Yeah, I definitely agree with that.
The Vmin is pretty low, so...
Ah, there we go. Right, so remember with a bipolar transistor, what is the V star? What is that set by?
VT.
Yeah, it's just set by KT over Q, right? In other words, it's something like 50 millivolts or 25. Well, it's
20.
The way we defined it, I believe it's 50 millivolts. KT over Q is 25 millivolts. There's just a factor of 2 there in terms of relating the GM and the V star. But basically, it's really, really small, right? In other words, it's the smallest it possibly could be for anything that looks like this. Why is that bad news? From the standpoint of particularly this.
A lot of noise.
More noise current.
Yeah, why? I mean, what's the sort of small signal parameter that's making it have a lot of noise?
Okay.
I heard somebody say it. Small V star means large what?
GM.
Yeah, GM, right? So basically with a bipolar, even if I solve all the other problems that we talked about, I'm going to get a really big GM for that output device, right? And that's rather unfortunate because I just want the thing to be a current source, right? I don't want to be adding a bunch of noise. So it's kind of useless for me to have that GM, right? Well, so instead what people will typically do, and by the way, you can play this same trick in MOSFETs as well, is you essentially intentionally degenerate those current sources, right? So by the way, I'm sure everybody has seen source degeneration before. Raise your hand. Okay, good, right? So simple idea, you just stick the resistors in the source. If you make that resistor big enough, essentially the GM you get from that device in the limit becomes 1 over the source resistance, right? So it's just a way of basically reducing the effective GM of that transistor, okay? And in case you don't believe me, you can walk through sort of these calculations here. I'm not going to bother doing it because it's fairly straightforward. But basically, as you increase that source resistance, the noise you're going to get is going to become closer and closer to just the noise from that RE, or that source to generation resistance. Okay? But now if you kind of think about it, this is again kind of getting into the trade-off that we had just touched upon, which is if I have some bias current flowing through here, as I increase that resistance, I'm going to get some voltage drop across there, right? That basically means the Vmin I can use across the whole structure is going to have to go up, right? So even though I can use this to reduce the GM, and therefore reduce the noise, I have to pay for it by increasing the voltage headroom across the device, okay? So just like with the MOSFETs, I again basically have this trade-off between how much voltage headroom do I use and how much noise am I going to get coming out of my bias current, okay? Now, it actually turns out, again, you can use this with your MOSFETs as well. And in fact, for at least a certain range of voltage, you can show that this particular structure has the lowest noise for a given Vmin across it. Okay, and you can actually optimize sort of, what RE you should use to do that. But again, the bottom line is, if I give you a more, a larger Vmin, you're going to be able to get lower current. But of course, you're also going to have lower swing. Okay, so really the name of the game is always going to be, how do you choose between voltage swing and lower noise? Okay? Does this make sense to people? Or? Okay. So I'm going to take sort of a little bit of a break from noise because we've been beating on that, quite substantially for a while now. And just talk a little bit about sort of how can we actually get even better current sources, at least from the standpoint of DC output resistance. And then we'll come back and talk a little bit about noise again towards the end of that. So, as again, I'm sure you guys have seen many, many times before. Let's say that I can't really actually get the output resistance that I wanted, which as some of you guys actually complained about in this homework, you couldn't quite get the output resistance you wanted. Well, simple trick to play is obviously add in the cascode, right? Now, just to make sure it's sort of absolutely clear to everybody, what I'd like to do is just come up with a very sort of simple, intuitive explanation as to why a cascode helps with output resistance. So, you guys tell me, what's so great about cascodes that it makes the output resistance better than it used to be? Why is it that, so many times you're told that thing on the left right there is so much better than the thing on the right?
Fixes the VDS of M1.
Ah, okay. So
RO is proportional to 1 over lambda, and so if VDS doesn't move with current, then...
Okay, there we go. So Will, basically, I should have you draw the picture then. So, at least the way I like to think about it, and I guess Will does as well, but, hopefully you guys will agree with us. Basically, what you're doing by adding this cascode in here is you're trying to fix that VDS, okay? Or let's call it actually VX for now, right? Because if I can keep that basically fixed, if I again just draw, let's say, my IV characteristic, something like this, right? If before I had a certain range of voltage that I moved, that translates into, of course, a certain change in current. But if I can just reduce that range in voltage, then obviously the change in current is also going to get smaller, right? So really all a cascode is trying to do is reduce the amount of change in voltage right here, okay? So just to be, very explicit, let's say I had plus minus 100 millivolts of change at V out over here. If I add that cascode in, how much change would I get at that Vx? And somebody other than Will. What does the cascode do? Yeah?
It will be divided by the gain of the intrinsic gain of M2.
Yeah, exactly. So if that M2 has a gain of GM RO, then basically the voltage swing you'd get at Vx would be plus minus 100 millivolts. divided by GMRO. Okay? So by the way, keep this in mind because we're going to use that a little bit later on. So basically, whatever the voltage gain of that cascode device is, that's how much it's going to isolate the swing on the drain, meaning the swing over here, from the swing over there. Okay? So if we're going to be using cascodes, obviously I have to pay some voltage headroom to do this, right? And so the natural question that almost always comes up is just, okay, fine, so when do I really get the benefit? And if I'm going to do this, basically, how should I come up with this bias voltage over here? Okay, so let's just take a look at those two things really quickly. So first here, I'm just showing a plot of the output resistance. In blue here is the circuit with the cascode. In pink is the circuit just by itself, so just the bias, just the transistor essentially. And as you've kind of learned to expect, only if I get sort of more than a certain amount of voltage across it, do I really get some significant benefit from that cascode. Okay? But there's actually something sort of interesting to notice here, which I'm going to sort of go through in a little bit more detail right here. Okay, so for this particular plot, I just kind of pseudo-randomly chose some bias points. Right, because over here, this is just really set by the V star. Right, but you can kind of say, well, how should I choose what that Vx should be? Right? Because it seems like if I choose a different Vx, I can kind of move around when I get a good output resistance versus not. Right? And usually the way you're sort of taught this is, if you make that Vx too low, you'll scrunch the bottom device, right? It'll come out of saturation. But obviously if you make it too high, then you'd scrunch this top device over here. Okay? So let's just take a look at what might be a reasonable way for me to choose that Vx. Okay, so what I've done here, and again I'll just sort of redraw it. What I'm basically doing now is I'm assuming I have my cascode. So it has some bias voltage right over here. And what I'm really going to do is I'm just going to be changing the value of that Vx. Okay? So essentially I'm tweaking this VB2 right here in order to shift what Vx shows up essentially on the drain of that bottom device. Okay? And again, the way I'm going to do that is through that same K factor we had talked about earlier. So if K is 1, I'm just going to set that equal to the V star of the bottom device. If it's 2, it's 2 times V star, and so on and so forth. Okay? So basically what that would mean is that as I change that K, I'm changing this bias voltage right here. And again, as you'd maybe learned from 140, that's kind of moving around between which of the two transistors do I basically place into saturation, okay, for a given amount of voltage across it. So what I'm showing here is this red curve, that's with no cascode. This green, pink, and blue, that's basically me changing this K factor right here. So just to make it a little bit more clear, the bottom curve, that's with K of 0.5. This is with a K of 1. And this is with a K of 1.5. Okay? So now if we actually kind of look at this, this tells us a very interesting result, which, again, maybe some of you have actually seen before. So if I put some relatively small amount of voltage onto that thing, let's say less than 500 millivolts or so. By the way, this is not in our technology. This is in like a 0.35 micron technology, but you can take the numbers and sort of scale them or shift them appropriately. So basically notice if I put less than a certain amount of voltage in, doesn't really seem to matter all that much whether I used a cascode versus not. Nor does it seem to matter all that much what I really chose for this K, right? Because they're all sort of, everything's kind of converging to roughly the same curve right there, right? However, if I do actually get extra voltage onto it, now's where I start to see a difference, right? Once I actually put enough voltage on that thing, now it looks like basically the higher the K that I chose, at least, as I get to higher voltage, the higher the output resistance I can eventually get to, right? So that kind of tells us that actually we don't really have all that much to play with here, right? Because in some sense, you know, even if I choose a small k, it's not really going to give me any higher output resistance when I have lower voltage. It's actually going to give me basically the same output resistance as if I choose a larger k. So from a practical standpoint, the way you should really do this is basically just say, okay, fine. In general, I should basically just choose a high k value, meaning really make sure that that bottom device is in saturation. Because if I do that, then if I do ever get large voltage across it, I'll get the really nice output resistance, right? I'll get a much better output resistance than I would have if I chose a lower k, okay? But basically, there really isn't much penalty for doing that. So unlike what you maybe, you know, have heard from 140, basically, even if that cascode gets squashed out, the overall resistance you're going to get is never going to be worse than if you didn't have that cascode in there, or at least never really substantially worse. As long as you set the biasing on this such that you're basically sure that bottom device is actually going to be saturated. Okay? Does this kind of make sense to people, or? So basically from now on, and you know the way I typically do this, if I have a cascode and I need to sort of decide how to bias the thing up, I just bias it so that I get a pretty reasonable nominal voltage there. And then I know that basically across almost the entire space, you know, I'll never be worse off than just having the single device. And if I ever do get a large voltage, I really will get a large boost from that cascode. Okay? So by the way, this is kind of really good news because it says that, you know, all the stuff where we kind of hammered into you about 20 different ways of doing cascode biasing probably doesn't matter all that much. Okay? Because as long as you kind of get it roughly right, you'll probably get basically the output resistance you wanted, particularly at that, you know, once you actually squash the thing into the range where it really matters. Okay? So, because of that, I'm actually not going to spend almost any time at all talking about how you do high swing cascode biasing. I'm going to assume that you guys have seen that before. Okay? So, again, because really the point here is that, as you know, in most of the situations we're interested in, which is really when you're putting a low voltage across the cascode, the accuracy of that bias just doesn't really come into the picture all that much, right? Because I moved that thing around quite a bit, and they're all basically giving me the same output resistance. So it's important to make that accurate when you really have very large voltages, okay? But again, in practice, that's not typically going to be the case, okay? So I'm also going to assume that you've seen a bunch of these wide swing cascode things all over the place before. If not, just go back. You know, Grandmeyer has a long list of different cascode bias circuits and all the equations you can use to work out exactly what they're doing. But I'm not really going to spend too much time on it here. There is just one thing that I wanted to sort of mention. Here I'm sort of showing an example of a high swing bias for the cascode. There is one thing that I did want to mention. So if you'll notice here, when I built the current mirror, I put the cascode onto the mirror leg as well, right? So I just want, you know, just to be absolutely clear, why is it that I did that versus an example, and let's just say this, you know, let's call this V bias right here. Why did I build my mirror that way versus something like this? Process variations. Okay, yes, but why is this sort of quote unquote bad from the standpoint of process variations?
So the VTH might change, and then for each transistor it might be different each time, so you won't always have a fixed V bias that make it work.
Yeah, so that's true. So you said there's some process variations. You know, this V bias may not exactly give me the right thing. That's true, although notice I've generated that V bias from another transistor. So as long as, you know, all the VTHs shifted roughly in the same way, it would be kind of similar. And I also just argued that it didn't matter all that much from an output resistance standpoint exactly where I set that Vx, right? So why is it that I really wanted to do, that I really wanted to do this and not that? And you're right, it actually does have a lot to do with variation, but I'm not sure we've exactly nailed down the answer.
Is that going to be peaking?
Peaking. I'm not so you mean from a frequency domain standpoint?
From a DC standpoint, like, it kind of looks like a peaking current source.
Oh, okay, so I think I know what you mean, but that's, and that's actually related to the issue that I'm getting at, but, let me try and get something more specific, and then we'll come back to it, okay? Yeah?
The mirroring won't be same because the VDS is not the
There
same.
we go. That's really the answer, right? Now, you could sort of tie that back into peaking, but that's kind of what I was getting at, okay? So the real issue here is that basically, notice the VDS over here is definitely not the same as the VDS over there, right? And in fact, the output resistance of this is definitely not the same as the output resistance of that, right? So in some sense, I kind of claim that if I was to do this on the right here, that's breaking the #1 rule of matching. Okay, by the way, what is the #1 rule of matching? I said this back when we were talking about layout. What is that rule?
Make everything symmetric.
Or make everything exactly the same. Yes, right? So clearly this piece right here is not exactly the same as that piece right there, right? Yeah.
Why are there two current sources in this circuit?
Oh, so basically this, the trick here is that this one is in order to generate the bias voltage. You want to do that in a way that's relatively independent of the threshold. So the way you do that is you'd have to take a bias current and shove it through that device, right? So this leg right here, that's just like the V bias generation. This is kind of like my normal current mirror.
Okay.
Okay?
Gotcha.
By the way, how many of you guys have seen this particular V bias generation circuit before? Okay, good. Like I said, if you haven't seen a bunch of these before, just go grab Gray and Meyer. They'll tell you a long list of equations as to how you're supposed to go about doing that. Unfortunately, many of them are not exactly correct because the devices aren't quadratic. But again, the good news is you don't have to get that exactly right. As long as it's kind of close enough, you'll basically get the performance that you're interested in. What's more important, specifically from this example here is if you do have a current source with a cascode, make sure you build the mirror also with the cascode. Okay, because otherwise, just the mirroring ratio you get won't actually be correct, and maybe you're really clever and you try and do that to actually intentionally get extra current, but most of the time I would claim that you're better off just knowing what it is that you really get, and then you can play around with things afterwards. Okay? Any other questions on this, or? Okay. So, the last thing I want to spend a little bit of time on in terms of current sources is just, well, okay, we talked about cascoding. We said that's great because if I do a cascode, then now, if it used to be that if I just looked at over there, I got, let's say, something like RO. Now, if I add in a cascode, I can essentially make this GMRO times RO, right? In other words, I'm boosting the output resistance by sort of the gain of that cascode device. Well, sometimes you need really, really high output resistance. In particular, because maybe you want to get very, very high DC gain. Okay, and you might need to do that because if you want to build some feedback amplifier that very, very precisely tracks its input, that basically means you need very, very high open loop gain. Okay? Well, so one of the things you probably learned to do that is you say, okay, well, if the cascode works once, why don't I keep doing it, right? Why don't I just keep adding more and more cascodes? So let's say I had like, I don't know, a quadruple cascode or something like that. Well, yeah, that worked great back when we had like 15, 20 volt supplies, but these days not too happy, right? Because, this stack alone right here is probably my entire supply voltage, okay? So if we want to do something to still get higher output resistance, but not essentially give up on the voltage swing, we have to be a little bit more clever, okay? Well, the way we can be more clever is to remember, and this is actually why I went through it, remember the whole purpose of this cascode is to keep that Vx as fixed as you can possibly make it, right? Well, guess what? There's lots of other ways I can try and make Vx as fixed as possible. So, just as an example, or maybe I'll actually turn it over to you guys, if you wanted to make sure Vx was really, really fixed, conceptually, what kind of circuit would you try and build? Yeah, a feedback circuit, right? So conceptually what you do is something like the following. You take some reference voltage, which in this case is going to be kind of arbitrary, but pretend that you have that. I'll take, let's say, some op amp. And then essentially I'm going to try and tie some feedback circuit that makes that Vx as fixed as I can possibly make it, right? Well, in fact, the circuit we just drew is exactly a so-called gain-boosted cascode, okay? Because all this thing is doing is it's saying, okay, basically if there's any movement over here, that'll show up at the input of the op amp. The op amp will apply some gain to that, move the gate of the transistor around, and try and squash that movement, right? So, this is a little bit funny of a feedback circuit, but basically this is just a source follower in some sense, right? So I kind of have just an op amp driving a source follower. Okay, in other words, this whole thing just looks like a unity gain feedback loop. In other words, trying to force Vx to be equal to Vref, okay? And if you do that, indeed, you can get actually a higher RO. And notice I didn't stack any more transistors here, right? So the voltage swing should still basically be the same. So now, just to be sure it's clear, if I was to do something like what I've drawn right here, what would the RO of that be equal to? And let me call that, capital R out. So what would that R out actually be? Okay, well, so you made one assumption. So you assumed that I had an ideal op amp. If I had an ideal op amp, you're absolutely correct. But so now let me have not exactly an ideal op amp. Let me say that the gain of that thing is AV. Okay? So what is the R out I'm going to get?
Multiply by AV.
Yeah, basically. Right? Now, so to be more precise, and I want the more precise answer. You'll see why in 1 second. So if I was really to be precise, what would that answer be?
1 plus AV.
Yeah, there we go. 1 plus AV. Okay? So basically I'm going to get 1 plus AV times GMRO times RO. Right? Okay, and again, you'll see in 1 second why I wanted that 1 plus AV. Okay? Great. So I have this magic circuit, and let's say, I really did have infinite AV, I have infinite output resistance. Anything I should be worried about if I was actually going to try and build this thing?
Oscillation.
Ah, there we go. Right? I have a feedback loop. So anytime you do a feedback loop, the first thing, the first bell that should ring in your head is, oh, stability, right? Because no free lunch, right? You're going to do that, you got to worry about the stability. So let's take a look at what actually that's going to imply. So to do that, I'm just going to redraw the circuit here again. So I've got some Vref. I've got my, let's say, op amp, or really just an amplifier. That's going to drive the gate of the cascode. Take the feedback from that source node. And then this is going to be my current source, let's say just with some arbitrary V bias for now. Okay? So in order to look at stability, what do I basically have to know about? What are the sort of things I need to go and calculate?
Poles.
Yeah, I need to know something about the poles, right? Well, so the way I've drawn it, obviously there's no poles because there's no capacitors, but life's not that good. So let's just go and add in, let's say there's some CX right there, okay? And let's say there's some CG right there, okay? So now if I'm interested in stability, like we just said, we need to figure out the poles. And to make my life easy, let's go and try and figure out kind of the open loop poles. So when I say open loop, what I mean is, as an example, and I'll draw it in a different color, As an example, let's say we just broke the feedback right there. And just let's say from, V in to V out. I just want to know what are the poles that I'm going to pick up. Okay? So first of all, how many poles am I going to get?
2.
Yeah, 2, right? I've got 2 capacitors. So I'm going to get 1 pole from here, 1 pole from there. Okay, so it's going to turn out that figuring out pole number 2 is actually a little bit easier. So let's do that first. So for pole number 2, well, either A, so maybe we can do it quickly. Who knows what that's going to be? And again, not Will. Not Shiva either. We've got to spread the participation here. What's pole number 2 going to be?
GM over CX.
Yeah, right? So basically, if I look up into the source of that transistor, the effective resistance I get is just 1 over GM, right? And let's actually be explicit. Let's call this M2. Let's call that M1. So basically, I'm going to get 1 over GM2 is the resistance. And just because I was sort of, not necessarily lazy, but since I just explicitly labeled the capacitor, of course, the capacitance is just Cx. So the pole is, of course, just 1 over R effective times Cx, which, of course, is going to give us GM2 over Cx. Okay? Should be no real surprise right there, right? So now, is that going to be at a high frequency or a low frequency? What do you guys think?
High frequency. Low.
Low. So I heard both versions, so maybe we'll take a vote. So who thinks it's going to be at a low frequency? High frequency? Okay, now why?
CX is probably pretty small.
Okay, what do you think CX actually is?
CDB.
Okay, there's some CDB in there. Anything else that looks like it might show up? Let's assume even, we have great transistors that you can't actually build, that have 0 drain and source area. Is there any, intrinsic capacitor that I could kind of lump as being part of CX?
CGS2.
Yeah, CGS, right? Roughly speaking, that's going to be CGS2. Okay? So now, that means that roughly the pole there is GM2 over CGS2. Anybody remember another name for that?
FT.
Yeah, it's omega T, right? Basically, that pole is roughly sitting at the FT or the omega T of the transistor. Okay? It's not really exactly just CGS, but it's close, right? Because I'm going to have a CGS just sitting like that, right? And fine, I have some drain parasitics there, and I have, the source to bulk. But ballpark, I can kind of lump all those together and say maybe they're like twice of CGS, right? Or maybe there's 50% of CGS. But ballpark, basically you just have CGS sitting there, right? Or maybe some factor times CGS.
But VG is not ground, right?
So I'm assuming the output resistance is sort of sufficiently low that it kind of looks just like CGS. You're right, it's not exactly that. But actually, that's only going to push the pole even higher, right? Because the effective capacitance would be even smaller. Okay, so ballpark, that's going to sit at omega T. So as long as I have sort of a halfway reasonable transistor, that should be at really high frequencies, right? Okay, well, so where's pole number 1 going to be? Okay, we can do the simple thing first. What's the capacitance for pole number 1?
CG.
Yeah, that's CG. Okay, so what's the resistance? I heard somebody say it. Let's just, pretend this thing inside of here is just a really stupid amplifier. So it's that, roughly speaking. So what's the resistance?
RO.
Yeah, it's just the RO, right? So basically the pole is just going to be 1 over RO times CG. Okay, well, so we just said pole number 2 should be at a pretty high frequency. And by the way, as we'll see in a little bit, you really want it to be at a high frequency for several different reasons. Pole number 1, that's just going to be RO times CG. If I have a good high gain amplifier, that RO is probably pretty big, right? So basically, pole number 1 looks like it's going to be at a low frequency. So if I want to make sure this thing is stable, what's kind of the criteria that I have to use? Or which way do you think I'm going to design this thing to make sure it really is stable?
Low frequency.
Low frequency. What has
The
to be low
pole.
frequency?
The pole.
Which pole?
1.
Yeah, so I'm going to place the first pole at a low frequency. By the way, by how low of a frequency is low frequency?
Phase margin.
Okay, yeah, phase margin. So what does that actually mean?
Decade or 2 below.
More than
Or
60
the
dB.
second pole.
Okay, so you said a decade or 2 or something like that. So good news is you guys are going to have a homework. You're going to have to tell me exactly what a decade or 2 actually means. Because guess what? It's actually going to depend on some other stuff, right? In particular, just to maybe push it to be to the extreme, let's say that was a gain of infinity. How far down should your pole be relative to omega t?
DC.
Yeah, it better be at 0, right? Because otherwise you ain't going to be stable. Okay, so again, you'll get to do this more in your homework, but basically you're going to set that first pole to be sufficiently low frequency compared to this internal node to make sure that loop there is stable. Yeah.
But the gain boosting needs to have more bandwidth than the signal it's modulating the drain of M2.
Okay, we're getting there in 1 second. So you're absolutely correct. Right, so we just said that basically omega P1 in some way has to be less than omega P2. But what Dan was just saying, which is absolutely correct, is, well, hang on, I'm actually trying to use this thing to actively boost my output resistance, right? And so if that thing is too slow, that's actually going to mess up the behavior of my circuit in terms of the way I want to use it. So what you're basically saying is there's actually a constraint on the other side as well. And that's absolutely correct. But just for people who maybe haven't seen this before, what I wanted to do is spend a little bit of time to just walk through what does the response of that circuit look like as a function of frequency, so we get an understanding of where that lower limit might actually come into the picture. Okay? Now, this one usually sort of has a lot of stuff going on, so sometimes people get a little bit confused, so we'll kind of go through it kind of piece by piece. Okay, so I'm again just going to redraw the circuit itself that we're looking at. There's again just our gain boosted cascode over here. Okay? And so in order to actually get at what Dan was talking about, what I want to look at is what is the output impedance of that structure as a function of frequency. Okay? But still remembering there's actually some load capacitance in that internal node. There's some capacitance sitting right there. And as I'll show in 1 second, and I'll do it in a different color, I'm also going to add a capacitor at the output as well. Okay? So we're going to take a look at how the behavior of this whole thing basically looks like as a function of frequency. Okay? So this is going to be sort of my standard Bode plot, and I'm doing it big because, again, there's going to be a bunch of stuff happening here. So let's say that's the log of frequency, and that's the magnitude of the output impedance. And I'll do that again in dB. Okay, so let's just go at this kind of piece by piece. So let's say I just had that bottom transistor right there. Okay? So if I just had that bottom transistor, then I would just get an RO of output impedance, right? So let's go ahead and do that in, I don't know, red. Okay, so just the transistor by itself, that's just RO, right? Okay, so now, let's say that I just add the cascode, but I don't have any gain boosting in it. Okay, so now what I'm going to add in is just essentially that device, and I'm going to remember there's some parasitic capacitance sitting right there. What's that going to do to my output impedance? What's that going to look like as a function of frequency? Or maybe first, just at DC, what output resistance am I going to get? Not Will. Come on, what's the DC output resistance of a cascode?
GMRO squared.
There we go. It's basically just GMRO squared. So to be more precise, and again, I'll do this. Let's say the bottom one, this is M1. That's M2, right? So I'm going to have RO1. And let's do this in, I don't know, blue. Okay, so if I add the cascode, I'm going to have GM2 RO2 times RO1, right? Now, is that going to stay at that resistance until infinite frequency, or no? It's not, right? Eventually, that cap over here is going to kick in. And essentially, what you're going to get is something that rolls down like that, right? And in fact, if I took that same capacitor and put it in parallel with the RO, you'd actually get something that also the RO would actually go down. So let me draw that too. Right? Okay, so now I've got the cascode. So now let me go and add in the gain boosting. Okay, and let me do that in yet again another different color. So let's say, I don't know, let's go with black now. Okay, so once I add in that gain boost, what did we say happens at DC to that resistance? Yeah, it's going to be 1 plus AV times GM2 RO2 RO1, right? Okay, so that's what I'm going to get at DC. Now, we said that when we design that loop, we're going to make the pole sitting at that node the dominant pole, right? So what's going to happen once that pole kicks in? How's the output impedance going to start changing? By the way, when we say that a pole kicks in there, what does that mean happens to AV?
Drops somewhere.
Yeah, AV drops, right? So if AV drops, what happens to the impedance? It also drops, right? So basically, wherever that pole is, we're also going to get a pole in the output impedance. Okay, so let's actually draw that. So now I've got a pole there. Now I actually sort of stopped in a cleverly, or strategically placed location. So what's going to happen if I keep going, more and more in frequency beyond that point? So beyond actually, let's say this point right here. What's going to happen to the black curve? Is it going to keep going down, or is something else going to happen?
40 dB per decade.
Not quite.
It'll flat out.
Yeah, it's going to flatten out, right? So why is it that it flattens out?
1 plus AV.
Yeah, exactly, right? So this point right here, that frequency, that's the point at which AV is basically about 1, or maybe a little bit less than 1, right? Because remember, even if I made AV 0, I'd still get the natural cascode, right? So that means that once that black curve meets the blue curve, it's just going to flatten out, right? By the way, that means there's a 0 in the transfer function. Okay, and just mathematically, if you don't believe me, just take this function right here, put a pole in AV, and when you do 1 plus AV, you'll get a 0. Okay? So by the way, in your next homework, you're going to be having lots of fun with poles and zeros because these things are going to pop up all over the place. Okay? So just like we just said, essentially, once we hit the point where those two curves intersect, now you're just going to basically track along with those curves. Okay? Okay, so now now we're finally actually ready to do something really quote-unquote useful for this circuit. because we're not just going to have this by itself, but actually there's going to be some capacitor at the output as well, right? So now what I want to do is figure out what happens to the overall impedance if I add that capacitor in. Okay, so to see that, let's assume that the capacitor, if I just draw the magnitude of the impedance of the capacitor, let's say it looks something like this. Okay, so that's 1 over omega c. Okay, that's where that c is this CL right here. Okay? And so just one last color to, make everything really clear. Let's go with green. Okay, so now if I take that gain-boosted cascode, which by itself had the black curve, and I put it in parallel with a capacitor, well, what do you guys think is going to happen? What is this thing going to look like? And actually, let me just do one thing really quickly just to make it a little bit more clear in terms of what's, oops. Let me get my axis back here. Just to make this really clear, I'm just going to move this to be right around there. Okay, and you'll see why I did that in 1 second. Okay, so let's say that was my capacitor curve. Okay? So now, if I'm going to draw the gain-boosted cascode in parallel with that capacitor, well, so initially, that should be easy, right? I've just got, oh, hard to see. Here, I'll do a different color. Can you guys see that? Yeah, okay. So, initially, nothing should really change, right? I just get kind of the same thing. But now, when that capacitor hits it, we're actually going to get something sort of interesting. So I'm going to claim that what's really going to happen is something that looks a little bit like this. Okay? Oops. Okay, so now, if you guys are paying very close attention, you'll notice that I shifted this, basically the point where this starts going down, I shifted it to the left a little bit. And what I also did was I drew this little kink happening right over here. Okay? So, what was going on there? Well, anytime I have some behavior like this, right? If I'm going to get a little kink in the curve from the output resistance, that same kink is actually going to show up even once I put that capacitor in parallel with it, right? Now, I've really exaggerated this because oftentimes if you really design the circuit right, if you did this in SPICE, you actually probably wouldn't even see that kink. It'd be like maybe smaller than the width of your line. But it does indeed exist, and it is actually important, okay? Because notice there's actually, if you sort of think about the poles and zeros here, there's two things that are happening. So first, right at that same spot right there, I'm going to get a 0, okay? But if you kind of think about it, the impedance could never be higher than the impedance of just the capacitor by itself, right? So what that also means is that basically right after I flatten out like that, I'm going to start tracking back down on the impedance of the capacitor, which basically means that right there, I'm going to have a pole. Okay? So, by the way, anybody know what a pole being spaced very closely to a 0 is called? Anybody ever heard of that?
Doublet.
Yeah, I basically have a pole 0 doublet. Okay? And so again, you have to really watch out for those, because if they're closely spaced to each other, it can be really hard to actually even see. But turns out, from a performance standpoint, it might actually be very important. Okay? So, how do we know if it's going to be important? Well, let's actually just draw a picture here that shows what happens if I took my amplifier that, let's say, was using that gain-boosted cascode for a load. And now what I want to do is draw what would happen if I just put a step into that amplifier. Okay? So let's say this is my ideal step input. And then what I want to do is draw how does that thing respond in time. Okay? Well, remember, anytime you have poles, basically that means there's something with some exponential time constant, or that time constant is associated with that pole. Okay? And so if we look at that picture over there, it kind of looks like we have one pole right here and another pole sort of over here, right? Okay, well, so if I'm not careful, and I really do have these sort of so-called pole zero doublets, okay, then what you can actually get is a response that looks something like the following. So I may have the fast initial thing that, let's say, does something like this. But if I actually have another pole that's sitting at a pretty low frequency, but that's just hard to see because there's a zero nearby, what you would actually also get is another exponential response that may look something like this. And let me do it a little bit more carefully. May look something like that. Okay? Now, I've obviously sort of exaggerated this picture somewhat. But basically, this first one, that's at the quote-unquote fast pole, or the high-frequency pole. The second one, that's at the slow, low-frequency pole. Okay? So, why is this kind of a problem? Well, notice if this really was this big, and I wanted to make sure my amplifier settled to, let's say, within 0.01% of the final input step, if this thing is really slow, I'm going to have to wait for this thing to actually settle out, right? I'm going to have to wait until that slower thing actually makes it all the way there. Right? And probably when I designed this thing, I kind of designed it to make sure that this fast thing was fast enough. But if I didn't keep track of the slow piece, then actually that may end up setting my overall performance. So now, if we think about this in this context, where might I end up with something that could be slower than I intended it to be? What piece of this circuit might actually not track with going quite as fast as I really wanted it to? And not Dan. Or Will.
The VX?
Say that again?
The VX?
Is it just the I mean, you're kind of right, but is it really VX? Or what's the thing, if we go back over here, we said that VX, kind of the pole there was pretty high frequency, right? But I had to make this pole lower frequency in order to get the feedback loop to be stable, right? So actually, is it VX, or is it something else that may not be tracking quite as quickly as I want it to? What do you guys think?
The op amp?
Yeah, the op amp, right? Because basically I had to make this pole the dominant pole to get the feedback loop to be stable. So now notice, and actually maybe just to make it really clear, where do you guys think that pole is? Right here. What frequency is that at? What's that going to be set by?
Is that the bandwidth of the op amp?
Yeah, it's the gain bandwidth of the op amp, right? That thing right there is just going to be at the gain of the op amp divided by RO times CG, right? Where, again, that's the CG, and the RO is inside of that op amp, right? So notice, that point is also exactly where I'm going to get that pole zero doublet, right? So now if I was to take this whole thing, and I wanted to use it in somewhere where basically, let's say, I use that as a load and I want to tie that overall op amp into feedback, then I better make sure that this point right here, meaning that gain bandwidth of the op amp, is fast enough that this pole that's going to show up inside of there, or really that pole zero doublet, is at high enough frequency that it's never going to mess up the actual thing I care about, right? Because if it is, then now all of a sudden all my dynamics will be stuck by this, and not by the actual GM that I tried to build on the other side of it, right? So that's actually where that other side comes from. You remember I told you that there was going to be a lower bound on that omega P1? Well, that's really being set by the speed at which you're trying to operate the circuit. Okay? This kind of makes sense to people, or? So by the way, just so you know, you're going to be building or at least analyzing one of these things in very gory detail for homework number 3. So if you have a question, you should ask now. Okay, so I think we'll basically finish up with that today. So next time we'll kind of talk some more about how you can actually use this and what some of the noise implications are. So I'll see you guys on Thursday.